So today we are going to talk about energy absorption and emission of atoms. And before we start, we need to talk about what is the kind of energy that we are referring to here. And we are referring to electromagnetic radiation, which electromagnetic radiation is just a form of energy that exhibits wave-like behavior, meaning that it travels through space like a wave. And usually when we think about this form of energy, we think about light, but that is electromagnetic radiation right here. It's just energy that behaves like a wave. And then you've probably seen before the electromagnetic spectrum, which just shows all the different types of electromagnetic radiation based on ordered by their wavelengths and frequencies. And as you might notice looking at the electromagnetic spectrum right here, that as the wavelength of the electromagnetic radiation decreases, the frequency, which is shown at the top of the spectra, is actually increasing. So wavelength we represent with a lambda, and frequency we represent with the Greek letter nu, and these are inversely proportional. Which is important to keep in mind when we are thinking about how much energy a certain form of electromagnetic radiation might have. And we can't see most of these forms of electromagnetic radiation. The portion of the spectrum that we can see is the visible light portion, which is this small portion right here, the visible light portion. But we can detect all of these different forms of electromagnetic radiation with technology, which becomes important when we are talking about identifying types of elements, which we will talk more about later in this video. But before we start, it's important to understand the different contributions made by scientists that allows for our current understanding of absorption and emission of atoms. So there are a few scientists that are important to note. Max Planck was the first person to come up with the theory that atoms don't just gain or lose any amount of energy, but rather that they can only gain or lose specific amounts of energy. And he put a name to this minimum amount of energy that could be gained or lost by an atom, and he called it the quantum. So a quantum is just the minimum amount of energy that can be gained or lost by the atom. And that was contributed by Planck. And then after Planck, Albert Einstein made some important contributions to our understanding of atomic absorption and emission. And his contribution was mainly to explain something that had puzzled scientists for quite some time, which is called the photoelectric effect. Scientists had been observing this, and what they observed with the photoelectric effect ultimately was not what they expected to observe. The photoelectric effect happens when electrons are emitted from the surface of a metal when light of some minimum frequency shines on that metal. And what they were observing is that once you hit this minimum threshold of energy, electrons would start to be emitted, but before you hit that minimum threshold, no electrons would be emitted at all. And Albert Einstein said that to explain this, we have to think about light not just as a wave, but also as a particle. And so he gave a name to this light particle, and he called it the photon. And a photon is just a light particle carrying one quantum of energy. And so Einstein's concept that light could be both a wave and a particle, we call wave-particle duality, meaning that it has both the nature of wave and the nature of a particle. And Einstein's theory didn't really have any experimental evidence to back it up, which is where Thomas Young comes in. He was the first person to demonstrate through an experiment the wave-particle nature of light. And his experiment is pretty complex, and you can look it up if you are interested, but it was called the double-slit experiment. So it's important that we give credit to these people who contributed to our understanding of this important theory. So let's talk about what this has to do with electrons. So electrons of an atom, we've discussed before that they are lazy and they want to stay at the lowest possible energy level that they can. But electrons in the valence shell of an atom can jump. We refer to this as a jump. It's an atomic jump, but they can jump to a higher energy level when they absorb energy. Absorb is kind of a small blank here. When they absorb energy. So we have names for the lowest possible energy level, and then the energy levels that electrons jump to when they absorb this energy, and we call the lowest available energy state the ground state. Ground state. And we call any quantum state that exists higher than the ground state, we call that an excited state. So the electron has gained energy, and we refer to that electron as in an excited state. And I'm not going to be able to fit this all in here, but excited state is any quantum state that has higher energy than the ground state. But as you can imagine, electrons can't stay excited forever. I mean, you yourself can go run laps around the track if you are really excited, but eventually you lose all this extra energy and you fall back to your lazy state or your ground state. And so when electrons lose this extra energy, we say that they emit, E-M-I-T, energy. So when electrons jump between energy levels, they can only exist either at an excited state or a ground state. They can't exist in between these states. And so for electrons to jump and make these jumps between states, they have to absorb or emit the amount of energy that is the difference between the two energy states. So you have to have a certain amount of energy to get from level 1 to level 2, and so you have to gain this much to get from here to there. So they have to absorb exactly the right amount of energy to make the transition. So we can picture these absorptions and emissions better when we look at a Bohr model and we think about where electrons are. So maybe the valence electrons of this particular atom are in energy level 2, and one of these electrons gains some energy from coming in, and it becomes excited and jumps up into the excited state because it gains exactly enough energy to get from this energy level into the next energy level. So that specific amount of energy has a particular wavelength, and scientists, we can measure this wavelength, and we call that amount of energy and the wavelength of that type of energy the absorption spectra of the atom. And then when the electron needs to lose the energy and come back down, it has to emit a light particle with a certain amount of energy, and we call the wavelength of that, the set of wavelengths of those energies, the emission spectra of the atom. So these absorption and emission spectra are super useful to scientists because they can be used to identify samples that are unknown. Each element has a specific set of wavelengths that it absorbs when light is shown through the sample. The sample absorbs certain colors of light, and so we don't see those colors of light once the light passes through the sample and the remainder of the light passes through the prism. We have gaps in our spectra because some of the light was absorbed by our sample. So that is an absorption spectra, the set of frequencies of electromagnetic radiation absorbed by atoms is our absorption spectra. Absorption. And then the emission spectra is kind of the opposite. The electrons are already excited in a hot gas, and then when the electrons fall back to ground state, they emit photons of light at specific wavelengths, and that light passes through a prism, and we only see the specific colors of light that are being emitted by that sample. So we see a black spectrum with just lines of color that are being emitted. And if we were to put those two things together, we would have what's called a continuous spectrum, which is what you obtain when white light passes through a prism and you see a full rainbow of colors. So the set of frequencies of electromagnetic radiation emitted by atoms of a particular element is emission spectra. Emission. So let's try putting this to use. If we look at all these different spectra here of different known element spectra, and then we have our unknown spectra down here, we can figure out what our unknown sample is likely to be just by comparing it to the other spectra. So take a second and look at this, and you could pause the video if you want to try and figure it out on your own, and figure out which of these spectra the unknown sample looks the most similar to. And if you start looking at it, you notice that there are certain lines that just line up with one of the spectra. So this purple line lines right up with Mercury, and you can see the purple lines of some of the other spectra too. But then when you go and look at all the other lines, you'll find that the lines that line up almost perfectly with Mercury's spectrum. So this unknown sample is most likely to contain Mercury.